have not specified the interval here, is it? I have only specified one point of interval. Let's say your interval is, let's say you are having this x belongs to some 0 to a, and a can be either infinite or finite. Okay? Yes. What is your problem? So this was the initial, we're working out the initial, the Green's functions of this initial value differential equation. Okay? So we figured out yesterday for, let's say, x less, okay? In this very region, the Green's function is actually 0. Is that true? Is it true? Yesterday we have figured out in x less than t, okay? So this t is not actually 0. I told actually t is equal to 0. T is not 0. T is some point, okay? You can have t like this thing. Let's say it is greater than 0. Okay, it's in between here. Huh? I mean, you bisected this interval. Okay, so you are having only boundary condition at where? At one of the points, not at the other points. Clear? So that's why you are having in this very region x less than t. So that, okay, so you split it. Let's say 0 and t and t a, you split it. So you in this very domain. Okay? So your Green's function is 0. Clear? Because you start with, I have not actually specified the interval yesterday. So actually the interval looks like this thing. The initial point and the final point. Final point can be infinite. Is it? Clear? Got it? So this was an error in yesterday's problem. No? So rest of things are same. Okay, now let's take another way to derive the Green's function. So let's take the simplest of, although it's not simplest, this one example. So you are having this Poisson equation, is it? Okay. So let's take this Poisson equation. What is it equal to? Minus 4 by rho. Clear? So this is the Poisson equation. So let's figure out its Green's function in a simpler way. So I will show you the method first, then we will take another example. Clear? So the boundary condition is not specified. So the boundary condition can be here in this problem. Okay, so the boundary condition, what we can think as a condition defined at infinity. Okay, so in this very case, so you are having phi is defined at infinity, is it? On the boundary. This can be 0 on the boundary, or this can be non-zero on the boundary. Phi can be 0 on the boundary, or its derivative can be 0 on the boundary. That is field. Clear? So this is how we specify the boundary condition. Now let's say if you are having these kind of problems where the boundary condition is specified at infinity, okay, or at the boundary, how to solve them? There is a technique we do using the Fourier transforms. Okay, so I will show in detail. Okay, before that, so this is an inhomogeneous differential equation, a second order differential equation. Is it? Is it true? Okay. First tell me, is this differential equation self-adjoint? Is this a self-adjoint differential equation? Yes. Okay, it's a Laplacian. Laplacian is a self-adjoint differential equation. Okay. Okay. So now let's take. We need to figure out the Green's function. Let's try g of r prime. What I need to solve for? So what it should be? A delta function. Okay. So let's try delta r minus r prime. So what I will do? Okay, I'll put this minus sign here. So that means I'm having minus like this. Clear? Is it the same thing? Just I have changed the minus so that I can define. Okay, now if you are having a Poisson equation, Abass square 5 minus times, you introduce actually minus sign here. Got it? So much now? Can I do it that way? Okay. So I will write now. So you introduce actually minus sign because you are having a minus sign. Okay? Clear? So usually if you are okay, we started with differential equation where this we assumed okay, there was no sign. Whether that would have been negative or positive, we haven't taken that factor into account. Okay? So I have taken into account this minus sign explicitly here. Clear? So it is the same thing what we had done earlier. Okay, now tell me what is the function, the double derivative of that function yields me a delta function. Okay, so now tell me how I define a delta function. Is this? Is it a delta function? Is this a delta function first time? Huh? Is this a delta function? Isn't it? Last time we have seen. Yeah, huh? So now tell me what is the Green's function. Okay, so I will take this 4 pi here. So in my notation I will take 4 pi here. I'm sorry. So just I will take this factor. So this is a source term. This minus 4 pi I will take here. So this will be simply as. So what is the Green's function now? So it is simply. Now tell me, is this a minus 4 pi? Yes, it's a minus 4 pi. So what is the Green's function now? It's a simple way, is it? So we know the differentiation double derivative, okay? A Laplacian acting on 1 divided by r, so it gives me a delta function, is it? So what is the Green's function therefore? So that's actually same as g of r minus r prime. So as 1y, because this is a factor that depends only on what? The difference between the two vectors. Distance. Clear? So if you write now, so is this a translationally invariant system? So when the distance occurs as the, let's say you are having a coordinate of one point and the coordinate of another point, or the position vectors are specified, the function depends, let's say, on the difference between the two. That means it depends on the distance between the two, is it? So is that factor a translationally invariant factor? If you translate your coordinate system, distance will remain always fixed, is it? So that means your system is a translationally invariant system. So in translationally invariant systems, so the Green's function will be dependent on this r minus r prime. Okay, got it? So it will be simply the difference between, or rather it will depend on the relative coordinate. Clear? So this is the simplest of way to look at the Green's function. So this is a Green's function corresponding to what? If you see, it's actually corresponding to a point charge. Is it? Because we have solved what? What do we have solved? A differential equation for a point charge, is it? Then you can figure out what is the solution. What will be the solution? Now what is the solution? Phi of r, is it? So it will be simply d of r prime, g of r minus r prime, and then rho of r prime. What is your g of r prime? Okay, what is that? So I am. Is that true? So is this a potential? Huh? Clear? So this is how we calculate the potential if the charge density is given. Huh? Okay, so now let's calculate this in a different way. This Green's function. Okay? Using the Fourier transform. So I am having this very equation. Delta r minus r. Clear? So let's take in the 3 dimensions. So it will be actually r minus r prime. So we'll be solving it using the Fourier transform. Now what is, okay, what is the Fourier transform of, okay, Fourier transform of delta function? Okay, delta function, how we write the delta function? Anybody? Do you have an idea how we write the delta function in terms of the Fourier transforms? Okay, just do it. So if you are having a delta function, so one dimensional delta function, it's like this. dk by 2 pi e raised by I e. Okay, so it can be plus minus. There is no problem. For delta function, it will be both plus as well as minus. So there is no problem with that. Okay. So this is a one-dimensional delta function. So if you are having now a three-dimensional delta function, let's say, So therefore I can write this r minus r prime. So it will be simply as minus infinity plus infinity. So this is actually the so it is 2 pi cube e raised for I k dot r minus r. Clear? So this is how in 3 dimensions we write it, the delta function. Now let's take the let's take the Fourier transform of G. So let me write the Fourier transform of this G of r prime. So it will be in 3 dimensions g3k by 2 pi cube. Okay, so because it is g3k, so it will be over a volume. Huh? So you write g of k e raised to I k dot r minus r. So this is how we define the Fourier transform of a given function. Have you done it? Huh? Have you done Fourier transformers? Huh? Have you done it? First tell me, have you done it? Huh? Yes? आप कर रहे हैं Fourier transform. Okay, good. So now let's substitute these. Okay, so we will convert this differential equation to a Fourier space. Okay, or in other words, to the K space, because I am going from this R space, coordinate space to the K space. Now let's apply. So I will write now this nebula square G of r prime. Okay. So this nebula square will act on this thing. Okay. So for this G, so it is g3k by 2 pi cube. So I will go slowly in this very problem. Okay. A raised for I k dot r minus r prime. So this is a vector, this k here. Okay. Then you are having minus 4 pi. Okay, for delta function you are having g3k divided by 2 pi cube. Okay, e raised for I k dot r minus r prime. Okay, so now this is the differentiation with respect to x, is it? Or differentiation with respect to r, you can think. So now this will act on this r, not r prime. So this is a double derivative. When this will act on this thing, ik and ik factor will come down. Ik square factor, is it? So r I can write like this thing. g3k by 2 pi cube, okay, g of k, so then I am getting ik, okay, so it will be ik dot of ik, it's a vector, that's why I am putting dot, e raised for I k dot r minus r prime, so that's equal to minus 4 pi, this g3k by 2 pi cube. Okay, so now I can write like this. Let's club the two terms. So 2 pi cube. So I will be having simply minus k square g of k, and you take that here. So you will be having 4 pi like this thing. Then e raised for I k dot r minus r prime is equal to 0. Everybody followed it? What I have done? Everybody followed it? Huh? Okay. So since this is true for any this exponential, so it means this object has to be equal to 0. Okay, because these are all linearly independent things. So which implies therefore minus k square g of k plus 4 pi is equal to 0. Okay. So what it gives me? So we have figured out the Fourier transform of the Green's function. The Green's function in the momentum space. Okay, so that we have figured out in K space. Okay, whether this K is a momentum or something different, okay, let's not worry about that. So in K space, I have figured out the Green's function. Okay, so now let's substitute. Okay, so it's plus. It's a plus. Let's substitute this G of K in, because I am interested in G of r prime, Green's function in the coordinate space. So this is in the Fourier space, okay? This is Green's function in Fourier space that we have figured out, okay? Samajhaman? So you can think, okay, since yesterday I have told you Green's functions in physical situations represents the propagators, okay? So they are simply the transition amplitudes for a particle going from one point to the another point, okay? So you can think this as the propagator for the Coulomb potential. Clear? So if you are having a Coulomb potential, its propagator is this thing, this 4 pi by k square. It's in the momentum space, or you can think it's a Feynman propagator. More generally, we call it as a Feynman propagator in the momentum space. Got it? Okay. So now let's write that G of RR prime, okay, is equal to. So you are having G3k. G of RR prime you can think as the propagator in the coordinate space. Okay, what is G of? So it's 4 pi by k square e raised for I k dot r minus r prime. Okay, these things we will do again in quantum field theory. Okay, there will interpret these results in a more physical setting. So this is simply the mathematical derivation we are doing here. So it's 4 pi. Okay, so now let me convert. Since the problem is spherically symmetric, is it? Is that true? So okay. So now what I will do, I will convert this into the spherical polar coordinate G3k. So it will be 0 to infinity k square dk. Okay, so this 2 pi cube I will take out like this thing. So then you are having 0 to pi sine theta d theta. Then you are having 0 to 2 pi d phi. Okay, you are having this 1 by k square. Okay, e raised for I, this I can write e raised for I, okay, r cosine of theta, okay, where r is equal to magnitude of r minus r prime. Because this is k dot r, you will write it magnitude of k, magnitude of r minus r prime multiplied by cosine of theta. So that magnitude I have put as capital R, okay. So can anyone tell me how to do it? So you can do the phi integration. There is no phi dependence. So that will be 2 pi. So it is 8 pi square and it is 8 pi cube here. It will be simply 1 by pi. Okay. So it is 1 by pi. So this factor will give me actually 2 pi. Okay. Then you are having this k square goes. So 0 to infinity with dk. Okay. In this very factor, since there is an integration over theta, so I'll put in this very factor, put let's say r cosine of theta is equal to z. Okay, so what you will get? Sine of theta d theta is equal to minus dz by r. Okay, so once you will put here, so it will be here, then plus 1 and minus 1. This minus you will take inside, it will be simply minus 1 to plus 1. So these things you already know how to do it. So you are having 1 by pi 0 to infinity dk. Okay, then you are having integration over minus 1 to plus 1 dz e raised power I kz. Okay, so dz comes with a factor of r. Okay, like this. So now integrate it out. So it's simple integration. There is no hard it's not a hard integral. So what this will be? So you integrate it. So it will be e raised power I kz. E raised power I k. Okay, minus e raised power minus I k. So there is this r. You take it out. So there will be 1 by I k. Clear? So what it is equal to? So it is 2 divided by pi. Okay, 1 by r integral 0 to infinity dk sine of k by k. What is integration of sine x by x from 0 to infinity? So it's pi by 2. Okay, so the value of this very integral is equal to pi by 2. Now this pi by 2 will cancel it 2 by pi. So which class do you belong? It's not first time. First time is there. So it is simply 1 by r. Okay, so what is 1 by r? It's 1 divided by magnitude r minus. So we have figured out Green's function in a Fourier transform way. Clear? Huh? So this is actually, we have assumed a spherical symmetric problem. All the directions here, when we evaluated this d3k, we have considered all directions are equivalent. So you can integrate over the sphere, is it? But you can be having certain problems, let's say, where the z direction is, let's say, anisotropic to xy plane. Okay, you got my point? Then you need to, okay, that problem I am going to take. Let's think you are having a point charge inside some dielectric medium, okay, and the dielectric varies linearly with respect to z, only with the z coordinate. So that means the spherical symmetry is broken, is it? So in that condition, how we can calculate the Green's function? Okay, if I know the Green's function, then I can calculate the potential, is it? From the potential, I can calculate the electric field. Okay, so that problem I will take tomorrow. But let's take the another problem, doing the Fourier transform. Okay, so now you got how to figure out Green's function using the Fourier transform. Okay, so this is actually another way to solve the differential equations. Okay, so you can do actually using the Laplace transforms as well. Okay. So let's take this very problem. So you are having d2. Okay, this is. Okay, can you tell me what this equation corresponds to? It's a harmonic oscillator, is it? With driving. Here the inhomogeneous term f of t, it is simply the driving, is it? So source. So it drives the oscillator. It can be, let's say, some external field. Okay, it can be sinusoidal field. It can be any linear field, anything, any damn thing it can be. Let's forget about what exactly is that. So now let's try to figure out what Green's function of this problem. So what I need to solve? d2, okay, g of, let's say, t prime, I will take now. So let me write it this way. D. So I need to solve this very equation. Is equal to delta p minus d. So this is the equation we need to solve for Green's function. Clear? So I have not specified the boundary condition, is it? So you can think the boundary condition is defined at the infinity. Omega naught square. Yes, omega square. Clear? So we need to solve it. How to do it? So yesterday we have done this kind of problem. d2y by dx2 plus y, is it? There it was 1. Yesterday we have just, rather k square we have put. d2 by dx2 plus k square, g is equal to delta function, is it? So we have done yesterday it. So now we will do it in the using the Fourier transform. Okay. So how I will do it? So since it's a one-dimensional problem, I'll just use the one-dimensional Fourier transform. Okay. Clear? So the previous problem was a three-dimensional problem. It was actually involving the Laplacian, is it? Laplacian included all the three coordinates. So you could do that only in one dimension, but that will reduce to the same kind of differential equation, is it? With omega not equal to 0. Okay. So now let's take this g of t g prime. So it will be simply minus, now I will specify it. So it is gk by 2 pi. Rather I will put, instead of dk, I will write now, I will go to the omega space because time is related to the energy, is it? So solution one? Okay. So t, if I am taking this t as time, so it is related to the energy, clear? So let's call that energy as omega. So it will be g of omega e raised power, let's say I omega t minus 2 prime. Don't put this omega naught. So this omega naught is the frequency, natural frequency. So this is an integration variable. Clear? Okay, so you can put e, dE by 2 pi. So I will use omega. So what is now delta p minus t prime? So it will be simply minus infinity plus infinity, d omega by 2 pi, e raised power I omega t minus t prime. Okay, now let's substitute. So I will do now the direct things. So once you take the differentiation of over t, so it will act on this thing. So it will be minus omega square will come. Instead of this dt, okay, double derivative. So I will write minus omega square. Okay. So now plus, then you are having this omega naught square. It will not do anything. Instead of this g dt prime, you write simply g of omega. On this side, you are having plain delta function. So it is 1. Okay. So I have skipped those steps. You do it yourselves. What is your g of omega? So I'll put it as minus 1 divided by omega square minus omega naught square. Clear? Got it? I skipped all those steps, putting and everything. So, clear? So now let's use, so this is actually the Green's function where? Where it is? Huh? In omega space. Okay, now look here. One more interpretation to the Green's function. So if you are having Green's function defined in the energy space, let's think this omega is the energy space. The poles of the Green's function in energy space gives you the energy spectrum of the particle. Clear? What I mean by that? Where are the poles lying? Which is variable here? Omega is a variable, is it? It's an energy. Where are the poles of this very function? Okay, poles are at omega is equal to plus minus omega naught, is it? So what is the energy of the oscillator here? Huh? So let's think it as a harmonic oscillator. Okay, although it's a harmonic oscillator, is it? So it's a harmonic oscillator. What we can do? Okay, okay. Quantum mechanically it is simple to understand. So if you are in a harmonic oscillator, you can add an energy. So if you add the energy to the particle, it will go to the next level, is it? So you can add the energy to the particle, or you can take away the energy. How much you can do that? So it's exactly this much of frequency. So that means this object is actually the energy of the particle, this omega naught. So or you call it as a natural frequency, is it? Samajhan? You can excite the oscillations using this much of energy. Samajhan? So it gave me what? The poles of the Green's function gave me what? Huh? What did it give me? It simply gave me the energy spectrum of the system. Okay, so you are having this kind of system, its energy spectrum is given. Okay, so if I write it, let's write it in this way. 1 divided by twice omega naught, let's say 1 divided by omega minus omega naught minus 1 divided by omega plus omega naught. Can I write it? Huh? So it is plus, it's minus. Isha? Is it? So you are having two poles that I have identified here. So you can add energy to the at resonance, okay, or you can put where at off resonance. The system can be at resonance or at off resonance. How you can do that? Just put the energy same as omega naught, okay? Or you subtract omega naught. Clear? So this is the way we sometimes interpret this Green. Okay, forget about this interpretation. Okay, so let's substitute back to g of t this thing. So we are interested in this very factor. So I write this g of t prime, that is minus infinity plus infinity d omega by 2 pi. Okay, g of omega is actually, so I will take minus out, so it's 1 divided by omega square minus omega naught square t raised to I omega t minus pi. Okay, so now the poles are on the real axis, is it? So how to do the integration on the real axis? Last time I have told you. So you are having, this is imaginary of omega and this is real of omega. So this is omega plane. Isha? So omega is a variable. So it's where are the frequency? So this is omega equal to omega naught, and then you are having minus omega naught. So the frequencies are where? They are on the real axis. How to do the integration over real axis? No. How to do? You shift the poles. Either you shift both the poles to the up plane or pull them the down plane, or you can rotate it like this way. You shift this up, or you shift this, this up, you shift this down like this thing. You put it like this way and like this by infinitesimal amount. Okay. So this is the way how we do. I mean this kind of integration. If you are shifting this pole up and this pole down, so that means you are rotating this very axis, is it? So this rotation in complex plane is sometimes known as Wick rotation. Okay, W-I-C-K. So we call it as a Wick rotation. If we define now the contour in that way, so you'll be having, let's say, this shifted pole here, and shifted pole here, what will be the contour? It will be like this thing. Okay? So you will be having like this thing contour, is it? So this is sometimes known as the Feynman contour. Okay? Clear? So if I define my Green's, if I now integrate over that kind of contour, so this Green's function I call as the Feynman Green's function. So if you do now the other way around, so you shift both up, okay? Then you can take one contour like this thing in the upper half plane, or if once you shift them down, you can take the contour in the lower half plane, is it? So either you can do the contour here like this thing, okay? Or you can do like this thing, is it? So upper half plane and the lower half plane. You will see actually, if I evaluate it in this way, I will be having the both the contributions. So if I do only one half, okay, let's say if I do the integration only in this very plane, if I choose this very plane, the corresponding Green's function is known as a retarded Green's function. Okay, and if I do the integrate, okay, choose contour this way, then we call it as an advanced Green's function. Okay, I will tell you why the name is so. So now if I choose the Green's in this way, so I will be having both the components of the advanced as well as retarded Green's function. Okay, I will precisely define these terms in a moment. Now let's do the integration of this very thing in this way, along this very contour. Okay. So this is, okay, how to do it? Okay, I will write like this. So I will simply, I will complexify this object. So it's E raised for I omega t minus t prime divided by, I will write like this, omega square minus omega naught plus I delta whole square. Clear? I just complexified this, I mean the singularity, is it? Is it true? So it's like this thing. I will tell you how we usually do it. Okay. So you are having poles here. So omega naught square plus some I epsilon, let's say. Okay? So let's club these two terms together. So I can write it in this way now. Omega naught plus I delta whole square. Okay, so you are having omega square, then minus delta square. So it's an infinitesimal object. Okay, then you are having twice that omega epsilon, that I call as a delta. So much how delta square is actually 0. Huh? Got it? So much how? So this is how I do it. So now these things we have already done actually in the complex analysis. So now let me write it this object. So it will be 1 by twice omega naught, 1 divided by, okay, what it will be? Omega plus omega, sorry, omega minus. So let's make partial fractions. What it will be? What are the partial fractions here? So no. Have I done wrong anything? I think I should write a minus sign here instead of plus sign. So it's a minus sign. Okay, so what I will write? So anybody? Minus I delta, so it's omega naught, then minus 1 divided by omega plus omega naught. Is it clear? Is it clear? This very thing? Huh? So now if you see where are the poles here, now tell me why is one pole? Omega is equal to omega naught minus I delta. So that means this is shifted where? So this is the point. So omega is equal to omega naught minus I delta, and this is shifted where? Omega is equal to omega naught plus I delta. Is that true? Rather, sorry, minus omega naught plus I delta. Is it? So you are having now poles are shifted. So choosing this kind of, okay, so this minus I So everybody followed it. What I have done, I simply made a partial fraction of that very object there and utilized it this kind of contour. So now let's take the first factor. So let's take this very factor. So you are having first factor is minus infinity to plus infinity d omega by 2 pi e raised power I omega t minus t prime divided by omega minus omega naught plus I delta. Clear? So it is the first factor. Clear? So the first factor is like this thing. So now what I will do, okay, put omega minus omega naught is equal to z. Clear? So let's substitute this difference to be what? Equal to z. So what I will get? So minus infinity plus infinity dz divided by 2 pi. Okay? So it's e raised power I z t minus t prime. Okay? And there will be plus omega naught. So it's e raised power I omega naught t minus t prime divided by what it will be? Z plus I delta. Okay, okay, now you are having integration over z, is it? So this exponential is out of the integration, is it? Samajh aawa? So you are having this integral. Can you tell me what this integral is equal to? This is a standard integral. It's equal to certain function. Anybody? So you are having, okay, so minus infinity to plus infinity dz, okay, by 2 pi e raised power I z of t minus t prime, I should have written here, z plus I epsilon, okay, in the limit of epsilon tends to 0, because epsilon we can, this delta we can put equal to 0, so it is equal to minus I theta t minus t. Okay, so whatever is the object here, so you put a theta function. Samajh aawa? Got it? Huh? So what this object is? So this is simply minus I theta p minus t prime e raised power I omega naught p minus t prime. Okay, so now let's look at the second integral. Okay? Got it? Samajh aawa? Now look here, this is non-zero only when t is greater than t prime. Okay, so this is the part of the Green's function which is valid only which region? Let's say t prime is the earlier time and t is the final time. Okay, so that means if you think of a signal, it has come from past to the future, is it? Clear? So that means you are observing a particle which has come from the earlier time to the next time. You are having a cause earlier and effect later, is it? So there, in that sense, we call this as a retarded part of the Green's function. Or if you are having in this way, only, I mean, let's say, forget about if you don't have this very term. Okay, so you are having a Green's function that depends only where. So that is non-zero only at the final time. Okay, when the final time is less than the earlier time. Sorry, final time is greater than the earlier time. Okay, so the Green's function obtained in that way, we call it as a retarded Green's function. Okay, we call sometimes this signal as a retarded signal. Let's, for example, suppose let's say you are observing a signal that has come from some star, is it? So that star is far. Let's think of the sun. You get a signal from the sun, is it? The photon. How much earlier it has left there? 8 minutes earlier. So that means you are observing it 8 minutes after. So the signal you have received, it's a retarded signal. Got my point? So you can think, okay, so another, the opposite of the retarded is actually the advanced. Okay, you send actually signal from future to the past. So you are receiving usually signals from past to the future. So that's why we call it as a retarded sense, retarded Green's functions. Okay, so that's, these functions are very important for us. Okay, usually if we are doing the experiments, okay, retarded Green's functions are more important than the advanced ones. Okay, now let's look at the this part. Then you can appreciate the result. Okay, so let's take the another part. So minus infinity plus infinity d omega by 2 pi. Okay, e raised to power I omega t minus t prime. What I will do, I will take this minus sign here inside. So much more? Let me take this minus sign here. So it is minus omega naught plus I delta. So substitute, okay, put minus omega naught is equal to z. Clear? So much more? So what I will get? So this is equal to minus infinity to plus infinity, dz by 2 pi. Okay, what it will be? E raised to power I. For omega, what you will get? So now calculate omega. So it's minus z minus omega naught. Is that true? So it will be minus z, okay, minus I z, okay, t minus t prime, e raised to power minus I omega naught, t minus t prime, okay, divided by, okay, what you are having now? Z plus I delta. So what is that? So it is e raised to power minus I omega naught. So I will write, instead of this minus I can take inside, it will be simply t prime minus t, and you take this minus inside. So once you take this minus inside, it will be t prime minus t, is it? So now look at the formula. So that means the integration over z will give me simply theta t prime minus. So it means this object is only non-zero when t prime is greater than t. So samajh aa? So this is the component where the earlier time is what? So you are signaling, you are sending a signal from future to past, okay? So we call this as the advanced part of the Green's function. Okay. So this you can, okay, if you choose the contour in the lower half plane, for this differential equation, you will get only this part of the Green's function. If you choose where? In the upper half plane, you will get what? This part of the Green's function. But I am choosing the contour in such a way, I am including both the parts. So, got it? Okay. So let's write therefore Green's function. Therefore, g of t prime. So that will be same because it depends only on the difference, is it? So that is same as g of, because it's a time translation invariant system. So you are having the term. So what was here? So 1 by 2 pi was there, and there was minus 1 by 2 pi. Sorry, it is a minus I here. Minus I theta. So minus and minus plus. So I am getting like this thing: I divided by twice omega naught theta t minus t prime e raised to power I omega naught t minus t prime plus theta t prime minus t e raised to power I omega naught t minus t prime minus t. Okay, so this you can put, yes, we have actually figured out this Green's function yesterday, is it? I divided by 2k. I divided by 2k we have done, so you can write it like this thing. I divided by twice omega naught, and instead of putting theta function, e raised to power I omega naught mod of t minus t prime. Because it gives you the same concept, is it? Whether the mod is positive or negative, whether t is greater than t prime or t is less than t prime, is it? Then you can write these two terms. Clear? So this is the Green's function of the harmonic oscillator, or the Feynman-Green's function for the harmonic oscillator. Then you can calculate the solution, is it? So if the driving is given, okay, okay, so that will be the assignment for you people. Let's say f of p is equal to, let's say sine of t, sine of omega 1 of t. So you are driving at a different frequency. Instead of the natural frequency, what you are doing? You are driving at some different frequency. Clear? So what you will do? What is the solution therefore? Let's say you drive only from t omega 1 t only up to some pi, from 0 to pi. Okay? You are putting a signal only from where? 0 to pi. Okay? So that means t is from 0 to pi by omega 1. Clear? So this is this. Okay? Okay, let's take pi by 2. Okay, I'll take it with sine. Okay? So that means sine. So this f of t will be from where? 0 to 1. Clear? So now what are the limits? Time limits will be from 0 to pi by 2 omega. What will be the solution now? So let's write now solution. How we okay? Y of t, that's simply equal to, okay? So dt prime g of t minus t prime, okay? Then f of t prime. Now substitute, then you have to put the limits of integration from 0 to pi by twice omega of 1. Clear? Then you do all the integration. You know, huh? Samajh aawa? So you can do now the integration. Huh? So this will be the assignment for you people to figure out what is the solution. Okay. Then you will see actually you can appreciate if you are having a drawing harmonic oscillator at hand. Then you can see at what frequencies, what kind of frequencies we can add. We can get a finite solution and we can get a zero solution. Okay. Okay, so this is, now let's go to, so these were problems I mean in one dimension. Now let's go to m dimension. Many dimensions rather. Okay, so fetch me some water. Have you got it? Huh? We have just done only 2 problems, huh? Not more than that. Have you got it? Huh? Huh? Do you have any question? By the way, where are the rest of the students? Why they are not coming to the class? This stuff.